All right, today for 4.2. Okay, we're notice we have day 1 of 4.2. So we're going to be spending 2 days on this. Going to get my handwriting tools up here. Okay. Our objectives are to add and subtract matrices today, identify additive identity and inverse matrices, perform scalar matrix multiplication, and solve matrix equations. So these are the objectives for this section. We're going to be focusing on the first 2 today, adding and subtracting and identifying the additive identity and inverse matrices. All right, so first of all, we can have an equal matrices. Okay, so these have the same dimensions and they have equal corresponding elements. So remember, they're elements in the same relative position. So A is relative to 7. Okay, they're in the same position. And notice that it says they're equal. Okay, we can apply that. So we can say, all right, well then A equals 7. Because it says list the corresponding elements. We'll list them this way. We'll go ahead and list them as a equation. Okay, so then 2B, what's its corresponding element? Excuse me. Thank you, it's -8. So we'll say 2B is equal to -8. All right, how about D, or 3 here? What's the corresponding element to 3? All right, C minus 5. So we would say 3 equals C minus 5. Those 2 pieces are corresponding. And our last one, what corresponds with 3D? Good, D plus 6. So we could say 3D equals 3 plus 6. Sorry, D plus 6, my goodness. So D plus 6. 3D equals D plus 6. Those are the corresponding elements. And they're equal, which is why we can put the equal sign in between them. All right, so for example 1, it says find the values of A, B, C, and D such that. So we're actually going to take these and write some equations to actually solve them, which you've already written the equations, but still. Okay, so we know that to find the value of A equals 7. Well, wait a minute. That one was easy enough. We're done. Okay, B, we have 2B equals, what was it again? -8 is its corresponding one. So how would we solve for B? Perfect. We divide by 2, and we get B equals -4. Very nice work. So then for the next one, we have 3 equals, its corresponding element is C minus 5. How do we solve for C? Perfect. Add 5 to both sides. 3 plus 5 is 8 equals C. And the last one, D. So 3D is equal to its corresponding element, D plus 6. All right, so how will we solve this one? Good, we're going to subtract D from both sides. 3D minus D leaves us with 2D equals a positive 6. Divide by 2. D equals 3. So pretty nice stuff right there. It's like, woohoo, we can do this. All right, then let's move on down to addition and subtraction. Only matrices with the same dimensions can be added or subtracted, okay, because the way you add them. All right, because we add or subtract corresponding elements. This is why they have to be the same, okay, because we add and subtract the corresponding elements. So when it says we're going to add A plus B, A is a 2 by 3, B is a 2 by 3. Okay, so they have the same dimensions here. And the reason is because we're adding the corresponding elements. So we have to take 2 and we're adding it to 4. It's like if we set these on top of each other. So let me build our matrix here. And maybe it would be helpful if I kind of gridded it out, okay, because we're going to have 2 rows. So I cut it in 2, and we're going to have 3 columns. So I'm just trying to give you a way to see like what goes in position 1, 1. Okay, so it's going to be 2 plus 4, right? 1, 1, 1, corresponding element 1, 1. Okay, in the next one, element 1, 2, element 1, 2. So we're going to have 7 plus 2. The next one, element 1, 3 plus element 1, 3. So 0 plus negative 1. Now we're moving to the second row. So the first number is 3 in both of them. So 3 plus 1. The next number is 1 and a negative 2. So 1, 1 plus negative 2. And our last element is 5 and 3. So we're going to have 5 plus 3 here. So again, maybe having the grid is kind of helpful, maybe not. Okay, I made it a little bit big. So though, if I take that on and finish this, okay, so this is going to equal 2 plus 4 is 6 for my first one. 7 plus 2 is 9. 0 plus negative 1 is negative 1. Move to the second row. 3 plus 1 is 4. 1 plus negative 2 is negative 1. 5 plus 3 is 8. And that's it. Okay, this is our matrix. We evaluated the expression. So let's look at B. Okay, so we're going to do the same thing. And I'm going to go ahead and kind of grid it out again so we see all the spaces a little bit. Hopefully that helps. And we're just going to go in the same order, but this time we're doing A minus B. Also notice that order matters. Okay, if it was B minus A, we would have to write the 4 first and then the 2. But it's not. It's A minus B. So it's going to be 2 minus 4 in our first box. And then 1 over. It's going to be 7 minus 2. In our third one, 0 minus negative 1. Okay, so we've already done all the same work over here, right? It was just addition. So we're using the same exact numbers because they're still corresponding elements. They're in the same place on both matrix. We're just subtracting them. Okay, so next up we have 3 minus 1. And then 1 minus negative 2. And our last one, 5 minus 3. Okay, so that's what we're doing for our matrix. So this would equal 2 minus 4 is negative 2. 7 minus 2 is 5. 0 minus negative 1, remember that's plus a positive, so that's 1. 3 minus 1 is 2. 1 minus negative 2, that's the same thing as plus a positive, so 1 plus 2 is 3. 5 minus 3 is 2. So there is our final matrix. Okay, that is, we have evaluated the expression. Pretty sweet stuff there. The biggest thing with matrices is keeping it organized. If organization is something you struggle with, you're going to have to work really hard on this section with matrix because keeping it organized is going to be the key. Okay, then matrices have an additive identity and an additive inverse, just like real numbers do. Okay, so this column tells us about the real numbers. The additive identity for real numbers is a plus 0 equals a. Okay, so we're taking any number, A, we're adding 0 to it, and we're going to get that number back out. In the matrix, the additive identity is the same. Okay, it's where we're adding a matrix that doesn't change the original matrix. Okay, it's the same premise. We're going to come out with our original matrix. So the additive identity is always going to be a 0 matrix of whatever dimension, m times n dimensions. So we could have a 0 that's a 2 by 2. Notice every number in here is a 0. We can have a 0 or an O 3 by 1. Every number in there is a 0. A 0 1 by 4. Every number in it is a 0. Okay, so the additive identity or the identity matrix is a matrix of the same size. It does have to be the same size, but it's full of zeros. And it's called a 0 matrix. Can you believe it? It's nothing but zeros. It's a 0 matrix. Okay, the additive inverse then says if we take any number and we add its opposite, then it equals 0. Okay, so any number, 3 plus negative 3 equals 0. 7 plus negative 7 equals 0. The same premise stands for matrices. The additive inverse is denoted a negative A. Okay, notice it's got the negative in there. And each corresponding element is opposite. So we have our matrix plus our opposite matrix, or our additive inverse matrix, equals 0. And it's saying, it says every or each corresponding element is opposite. So look, here we have a 2. Now we have a negative 2. Where we had a negative 4, we changed it to a positive 4, the opposite number. Okay, where we had a 3, we changed it to a negative 3. Each element is its opposite because 2 plus negative 2 is 0. Negative 4 plus 4 is 0. 3 plus negative 3 is 0. 0 is just going to stay. There is no positive or negative. Okay, but the whole point is that if we take the matrix A and we add it to its opposite or its inverse matrix, we're going to get a sum that is a 0 matrix. Okay, if I add those together, I'm going to get a 0 matrix. Okay, so let's put this into practice. It'll probably make more sense. Example 3 says state the additive inverse and additive identity of each matrix. Okay, so we want to state the additive inverse and the additive identity. All right, the additive inverse, remember, is this last one that we did. So we're going to name it negative C equals, and it's going to be a 2 by 3 matrix. We're going to negate or make it the opposite of each of these. So if C, this element is 1, it's going to be negative 1. Then we have 0, it's going to stay 0. The next element is negative 6. The opposite of negative 6 is positive 6. Second row, the element is 9. The opposite is negative 9. The element is negative 2. The opposite is positive 2. The element is 5. The opposite is negative 5. Okay, there is your additive inverse. Then the additive identity of each matrix. So the additive identity is a 0 matrix. You're just going to make it the same dimensions and it's full of zeros. So it's a 2 by 3. So you have 3 zeros in the first row and 3 zeros in the second row. Ta-da! It is your additive identity matrix. You're probably like, this is the simplest math we've done all year, Mrs. Talbert. I wouldn't blame you. Okay, so for matrix M, same thing. Let's do the additive inverse. So negative M is going to equal, okay, this one is a 3 by 2. So I always do the column first instead of the row. I don't really know. So if we have 8, the inverse of that is negative 8. 7, so we're having negative 7. Second row, 6 is going to be, good, negative 6. Negative 5 is positive 5. Perfect. Third row, Negative 4 becomes positive 4. Positive 3 becomes, good, negative 3. There is your additive inverse matrix and your identity matrix. So name it O or 0 is going to be a 3 by 2 matrix of zeros. So kind of looks like a dice. That is all. That's your identity matrix, additive identity matrix. Okay, it does say, right? Let me move this up because we have a couple notes here to use. The addition of matrices is associative and commutative. Okay, but notice it says the addition, not the subtraction. Doesn't say anything else yet, just addition is associative and commutative, which is just like addition with real numbers. Okay, so some properties of matrix addition. We talked about the identity and the inverse. Okay, we're saying that they're commutative and associative. All right, and then we have this closure property that just says A plus B is an M times N matrix. Like it's going to be a closed matrix when we add them together. It's going to have dimensions. That's all that it means, that are closed in brackets. Okay. So we've kind of talked about all of these. Commutative means we can add in any order. Okay. Associative means we can group them, right? We can add A and B and then add C, or we can add B and C and then go back and add A. That's our associative. But addition is both of those things. All right, that is it for day 1. So I will see you tomorrow.